Somewhere out past the edge of our solar system right now, two small machines are floating in total darkness. Both left Earth in 1977. Both are still talking to us. And most people, when they think about this story, only think about one of them, Voyager 1, the famous one, the one carrying the golden record, the one everybody calls the farthest human object ever built. But there is a second spacecraft out there too. It gets far less attention. It flew a longer, harder road to reach interstellar space. And when it finally got there, it carried something its twin had lost decades earlier, a working instrument that let it see something Voyager 1 was never able to see. That spacecraft is Voyager 2, and this video is about why 2026 might be the most important year of its entire 49-year life. Voyager 2 actually left Earth first on August 20th, 1977, 16 days before Voyager 1 launched. The numbering has nothing to do with launch order. It has to do with which spacecraft was expected to reach its destinations first. Voyager 1 was placed on a quicker path, built to swing past Jupiter and Saturn, and then head almost straight out of the solar system. Voyager 2 was given something more ambitious, a route that would let it visit not 2, but 4 giant planets. To this day, no other spacecraft in history has done what Voyager 2 did. It remains the only machine ever built that has flown past all 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity to sling itself toward the next stop. Voyager 1 took the faster lane and left the plane of the solar system early, trading Uranus and Neptune for a closer pass by Saturn's moon Titan. Voyager 2 took the long way and paid for it in time. Voyager 1 reached interstellar space in August 2012. Voyager 2 didn't get there until November 5th, 2018, more than 6 years later. For those 6 years, Voyager 1 was already out there alone, sending back readings from beyond the sun's influence, and those readings were already strange enough to make scientists rethink their theories. But there was a problem, and almost nobody talks about it. Here's a fact that rarely makes it into the popular version of this story. The instrument best suited for measuring the edge of our solar system stopped working on Voyager 1 back in 1980. Not near interstellar space, not close to the crossing point. It failed before Voyager 1 had even reached Jupiter's orbit, decades before the spacecraft got anywhere near the heliosphere's edge. That instrument was the plasma science detector, built to directly measure the speed, temperature, and density of charged particles flowing both inside and outside the sun's protective bubble. Without it, when Voyager 1 finally crossed into interstellar space in 2012, scientists had to infer the plasma conditions using indirect clues. A cosmic ray counter here, a magnetic field reading there. They built an educated picture, but not a direct one. The single most useful tool for understanding the boundary had been silent for over 3 decades. Voyager 2's matching instrument never broke. It was still alive and working when Voyager 2 crossed into interstellar space in 2018, and that single fact changed everything. For 6 years, scientists on Earth had been reading data from the edge of the solar system while working with half a picture. What they didn't have was the most basic number of all, how fast the actual particles were moving, and how many of them there were on each side of that line. That gap sat in the Voyager dataset for 32 years, before Voyager 2 finally arrived to close it. When Voyager 2 crossed the heliopause, the invisible edge where the sun's solar wind gives way to the plasma between the stars, its plasma instrument recorded for the first time in history direct readings from both sides of that boundary during an actual crossing. Scientists published 5 papers about it together in the journal Nature Astronomy in November 2019, and the results were nothing like what the models had predicted. The boundary turned out to be much thicker than expected. Researchers had pictured the heliopause as a fairly narrow line, a clean handoff between hot solar wind pushing outward and colder interstellar plasma pressing in. Instead, Voyager 2 found a wide transitional layer, roughly 100 million miles across, sitting just beyond the boundary, in territory that was supposed to be pure interstellar space. Streams of interstellar particles were pushing inward through that zone, blending with solar material in a way no model had predicted. Voyager 1 had noticed something similar on its own approach years earlier, but the 2 spacecraft, crossing at different points years apart, described 2 different kinds of transition zones. The distance itself made no sense. Voyager 1 crossed at about 121, 6 astronomical units from the Sun, during a period of high solar activity. Voyager 2 crossed at about 119 astronomical units, during a period of low solar activity. Given how much solar activity was supposed to swell or shrink the heliosphere, those numbers should have been noticeably different. They weren't. Senior scientists on the mission admitted plainly that nobody has a solid explanation for why the boundary sat at almost the same distance regardless of the sun's activity level. The temperature drop was sharper than anyone expected too. Inside the heliosphere, the solar wind plasma is scorching, not in the everyday sense, but because its particles move at extreme speed, which is how hot is defined in plasma physics. Scientists expected a gradual cool down toward interstellar space. What Voyager 2 measured instead was an abrupt drop, happening across a much narrower stretch than the models predicted. Interstellar space itself turned out to be surprisingly crowded. Combining Voyager 1 and Voyager 2's readings gave researchers their first pair of direct density measurements from 2 points in space, showing that plasma just outside the heliosphere is more than 40 times denser than the solar wind at the boundary. Thanks to Voyager 2's working instrument, scientists could finally pin an actual number on the interstellar plasma's temperature, somewhere between 30,000 and 50,000 Kelvin. That's hot by everyday standards, but far cooler than the tens of millions of degrees measured just inside the boundary, and about half of what earlier theoretical estimates had guessed. And perhaps, strangest of all, the boundary leaks. The Voyager mission's longtime chief scientist called this the most remarkable discovery of the crossing. The heliopause isn't a sealed wall. Material crosses it in both directions. Voyager 1 had detected fingers of interstellar particles reaching inward through the boundary on its approach. Voyager 2, coming from a completely different angle years later, picked up something else. A steady trickle of low-energy particles leaking outward into interstellar space even before the spacecraft had technically crossed over. 2 different entry points, 2 different times in the solar cycle, 2 different leak patterns, but the same underlying truth. This boundary behaves less like a wall and more like a shoreline, with material washing across in both directions. The takeaway is simple to say but hard to fully absorb. The Voyager probes are showing us how our sun actually interacts with the material filling the space between stars in our galaxy. Not where the sun's influence cleanly stops, but how messily and continuously it blends into what's beyond it. Even now, both spacecraft are still sitting in a disturbed transitional region, not yet in fully undisturbed interstellar space, even at 13 and 16 billion miles from home. None of this happened by luck. Back in the 1970s, using computers far weaker than a modern phone, the people who designed the Voyager mission deliberately built it around 2 spacecraft instead of 1, so that a single set of readings from a single direction would never be the whole story. What the original planners couldn't have predicted was which spacecraft's plasma instrument would still be alive when the real moment of discovery arrived. Voyager 2's detector, the one tool best suited to filling the biggest gap in the Voyager 1 story, outlived its twin's matching instrument by more than 3 decades, and was still functioning when it mattered most. Step back from the interstellar science for a second and look at everything else Voyager 2 has done, because the list is almost hard to believe for a machine designed to last 4 years. It remains the only spacecraft ever to fly past Uranus. During its January 1986 flyby, it spotted 10 previously unknown moons and 2 new rings, measured the planet's bizarre 77-degree axial tilt, and found a magnetic field so wildly offset from the planet's spin axis that it still puzzles researchers today. It remains the only spacecraft ever to fly past Neptune. During its August 1989 flyby, the final planetary encounter of the entire Voyager program, it found 6 new moons, including Proteus, a moon large enough that it probably should have been spotted from Earth before Voyager arrived. It clocked supersonic winds on Neptune reaching roughly 2,400 kilometers per hour, the fastest ever measured in the solar system at that time. And it gave scientists their first close look at Triton, Neptune's largest moon, catching active nitrogen geysers, blasting material into its thin atmosphere, strong evidence that Triton was likely a captured Kuiper Belt object pulled into orbit by Neptune's gravity long ago. At Jupiter, it discovered a 14th moon and confirmed the active volcanic eruptions on Io that Voyager 1 had spotted first, watching one volcano throw a plume of sulfur dioxide frost 200 kilometers into space. It also returned detailed images of Europa's cracked, icy shell, images that hinted at a hidden liquid ocean beneath the surface and helped inspire decades of scientific interest in Europa as a possible home for life. Interest that eventually led to NASA's Europa Clipper mission flying today. At Saturn, it revealed ring structures far more complex than anything Earth-based telescopes had ever shown. All of that from a spacecraft launched on August 20th, 1977, 49 years ago, built with technology from before the internet, before GPS, before cell phones, designed to operate for 4 years, still transmitting data today. Right now, the team running the Voyager mission at NASA's Jet Propulsion Laboratory is focused on Voyager 2 more intensely than it has been in years, not because of anything new the spacecraft discovered, but because of something the team is about to attempt. Voyager 2 currently has 3 working science instruments: the plasma detector responsible for the historic 2018 crossing measurements, the magnetometer, and the plasma wave instrument. Together, they provide something nothing else in the history of astronomy can offer: continuous, real-time measurements of interstellar space, taken by a machine physically sitting inside that environment. But there's a ticking clock built into the mission that can't be stopped. Both Voyager spacecraft run on radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electricity. That decay is steady and costs each spacecraft roughly 4 watts of available power every year. At launch, each had about 470 watts to work with. Today, Voyager 2 has slightly more remaining power than Voyager 1, which is part of why it still has 3 active instruments, while Voyager 1 dropped to 2 after its low-energy charged particle instrument was shut down in April 2026. That power margin is thin and keeps shrinking, so engineers designed a bold fix, and they nicknamed it the Big Bang. The plan is a complete, simultaneous overhaul of how power flows through every remaining active system on the spacecraft, shutting some things off and switching others to lower power alternatives, all done in a single coordinated operation instead of one careful step at a time. Why do it all at once instead of gradually? Because the most dangerous moments in any power reconfiguration are the in-between ones, the brief stretches where the system is neither fully in its old setup nor fully in its new one. Those moments can trigger the spacecraft's automatic fault protection systems, which shut things down on their own the instant they sense the power draw exceeding what the generators can supply. By making every change at the same time, engineers hope to blast through that dangerous transition zone as fast as possible. This is all happening across a communication gap of more than 16 hours in each direction. A single command sent from Earth takes over 16 hours just to arrive, and any confirmation that it worked takes another 16 plus hours to come back. There is no live back and forth, no quick correction if something starts going wrong halfway through. It's an all-or-nothing move executed on a machine 13 billion miles from home. If it works, the payoff could be real, possibly a year or more of extra operational life for Voyager 2's remaining instruments. And if the procedure succeeds on Voyager 2, the same overhaul is planned for Voyager 1, no earlier than July 2026, with hope that success there might even allow engineers to bring the shut-down low-energy charged particle instrument back online. Voyager 2 goes first, not because it matters less, but because its slightly stronger power margin makes it the safer place to test something this risky for the first time. Every extra month these instruments survive is a month of data nothing else on Earth or in space can currently provide. And there is still a long list of unanswered questions sitting right at the edge of what these probes can tell us. Why does the heliopause sit at roughly the same distance from the Sun, no matter the solar activity level? What's actually causing particles to leak across the boundary in both directions? What shape is the heliosphere really? A long tail trailing behind the Sun like a comet's, or something closer to spherical? Voyager 1 and Voyager 2 are sampling 2 different points along that outer structure, and every additional data point helps narrow down which model is closer to reality. There's also the interstellar magnetic field itself. Both spacecraft have measured it from their own positions, and the direction of that field carries clues about how our entire heliosphere is oriented relative to the galaxy's larger magnetic structure. Voyager 2's magnetometer, still active in 2026, keeps adding to that picture from the southern side of the heliosphere, a different vantage point than Voyager 1's readings from the north. And underneath all of it sits a bigger, quieter question. What happens once both spacecraft finally go dark for good? There is no successor mission already out there, no other instrument anywhere close to where these 2 machines currently sit, and there won't be one for decades. Whatever question the Voyager probes leave unanswered when their signals finally fade will simply stay unanswered until some future mission, not yet designed, not yet funded, eventually makes the same long journey. The team keeping all of this running is small, and it has always been small. Many of the original Voyager engineers retired long ago. The engineers who took their place had to learn programming languages and design philosophies from a different era of spacecraft engineering just to communicate with these machines the way they were built to be communicated with. This isn't knowledge found in a modern textbook. It lives inside a small group of people at a specific building at JPL, and it can't simply be reconstructed from old manuals once the last person carrying that knowledge retires. And yet, in the summer of 2026, that small team is still there, still sending commands across 13 billion miles of empty space, still waiting more than 16 hours for a reply, still weighing the same trade-off week after week. How much instrument capability can be preserved without risking the survival of the spacecraft itself? Put it all together, the leaking boundary, the unexpectedly dense and cooler interstellar plasma, the sharp temperature drop, the strange consistency in the heliosphere's size regardless of solar activity, and what emerges is a picture very different from what scientists expected before either spacecraft got there. Our solar system isn't a sealed bubble cut off from the rest of the galaxy. It's something messier and more alive than that, a boundary that bends, thickens, leaks, and shifts, constantly trading material with the interstellar medium around it. That picture exists because of 49 years of continuous operation, and one instrument that happened to survive long enough to catch it. Voyager 1 is the name most people know, but it was Voyager 2, quieter, slower to arrive, less talked about, that carried the working tool needed to actually measure what was happening at the edge, and gave humanity its first direct look at the temperature and density of the space between the stars. Right now, somewhere out past 13 billion miles, that signal is still traveling toward us, faint, stretched thin by distance, taking more than 16 hours just to arrive. And right now, NASA is attempting something on that spacecraft that has never been tried before at this distance, an all-at-once power overhaul with one shot and no second chance, a result that will shape not just what happens next for Voyager 2, but what becomes possible for Voyager 1 when its own turn comes in July. The story of what Voyager 2 found at the edge of our solar system is one of the most significant scientific results of the last decade, and it barely made headlines when it was first published back in 2019. This channel exists to change that, to walk through what these spacecraft actually measured, without exaggeration, without inventing anything the instruments didn't record, just the real findings explained at the depth they deserve. The Big Bang result is coming. The next major milestones for both spacecraft are coming. The attempt on Voyager 1 itself is coming in July. When those moments arrive, you'll want to already understand exactly what you're looking at, so make sure you're subscribed and stick around because the signal is still on its way.